Hi, welcome everybody. We are so happy to have you at our first event of Deep Space Dialogues. It's our newest virtual talk series from the Space Telescope Science Institute in Baltimore, Maryland. We welcome back all the viewers who have joined us along with Frank Summers in the Retired Public Lecture Series, and we welcome our new guest for this new event. We are reimagining this new series, and we really hope that you find it very engaging with plenty of opportunities to ask our speaker questions in real time. So tonight's conversation is going to focus on opening up a new frontier in transient science with the James Webb Space Telescope. My name is Dr. Quinn Hart. I'm from the Office of Public Outreach at the Space Telescope Science Institute, and we're going to be chatting with Dr. Justin Pierel from the Space Telescope Science Institute as well. So welcome, Justin.
Yeah.
He is currently, well, he grew up in rural Maine doing lots of stargazing. I can only imagine the dark skies there. He did his undergraduate work in math uh, how do you say the college name again? I'm sorry, I'm
Bowdoin
stuck.
College.
Bowdoin College. Then he spent time working at NASA using Landsat satellites to detect landslides. He went on to do his PhD work in physics at the University of South Carolina. And from there, he joined the research team at the Space Telescope Science Institute here in 2021. And he's currently a NASA Einstein Fellow. He'll tell more about that to you later in the segment here. And a fun fact about him, he loves to do a lot of reading about fantasy and sci-fi novels and playing disc golf. So thank you again, Justin, for coming and joining us on our first ever Deep Space Dialogue. So how's it going today for you? How's your day?
Great. Yeah, I'm excited to be here. Talk about some transients.
Great. Well, the title of your talk is Opening Up a New Frontier in Transient Science with James Webb Space Telescope. So I think a question that people have will be, what is a transient object? And is there only one kind? Or is there multiple kinds? Could you kind of share that with everybody?
Absolutely. Good place to start. So when you look up at the night sky, whether it's with your eyes or with a telescope, most of the things that you see are sort of static. Things like galaxies or stars that if you observe them for, say, days or years, they wouldn't really change much, meaning their brightness or their color, things like that. So transients are objects that do change. They undergo some sort of rapid change in brightness or color or their properties. So things like a star coming to the end of its life and exploding as a supernova, or maybe a star that's orbiting a black hole and gets eaten up and gives off a ton of light. Or it could just be some star that's undergoing some change in its life that's changing its brightness by day. So these are the things that we sort of focus on as transients, and the kind of interesting thing about them is that because they are changing, often they are only visible for a certain amount of time. You know, they brighten, they fade, and then you're no longer able to see them. So one of the that's reasons that they're called transients. They're only there for a certain amount of time, which makes it an exciting and sometimes difficult field to be studying in.
Okay, thanks. That was a really good overview of that word transients, because I know different language in the astronomy community can be a little bit challenging if you're not in the field completely. So if you're just joining us, I'm going to share my screen here. So again, this is our first virtual event in the new series called Deep Space Dialogues. And we're here, Justin Pierel is joining us here from the Space Telescope Science Institute. I'm your host, Quinn Hart, also at the Space Telescope Science Institute. And if you're not familiar with our organization, we're the Science and Mission Operations for James Webb. Now, this is a new format for us in terms of the name. So if you're tuning in, you've tuned into the right place. We are live streaming on our Space Telescope Science Institute YouTube account, which is at Space Telescope Vision here. And please make sure you subscribe so that you can learn about future events as well as hearing about different science from scientists such as Justin, as well as some visualization and videos. So again, this is what you're tuning into right now. So I'm going to stop and continue here with questions. So have we known about transits since people have been around? And if so, how did we know about them?
Yeah, so the information that we've gained about transients over time has increased exponentially, as you might imagine, but it does go back quite a long way. So all the way back to about 185 AD, some early astronomers did a very careful job at kind of cataloging the night sky. You know, they were really paying attention to all the stars. They didn't know about galaxies at the time, but and planets that were going across the night sky. They had a really good catalog of those objects. And in about 185, it was the first time that we have a documentation, at least, of one of them saying, "Hey, there's something new in the night sky," and this was all by eye. There were no telescopes. And so they called that a guest star, which appeared and stayed bright for a matter of months and then disappeared. And there were lots of kind of general theories about what that was. And even now we're not positive, but the guess is that that was a supernova. And it took quite a while for people to realize what those were, but there are a series of them over time that we have documentation of noticing a new star in the sky, basically. And that's, an example of an early transient.
And I think I recall hearing that they were bright enough to be seen in the daytime sky.
Yeah, these are objects that were, in some cases, nearly as bright as the moon. You know, maybe half or a quarter as bright as the moon. Yeah, we don't see many of those anymore. It's been quite a while. Finding a transient with the naked eye in general is difficult and
Mhm.
quite rare. And then, yeah, there's been a documentation over time of ones that were just extraordinarily bright that has not happened in our lifetime.
Um, do you know off the bat the last time a bright transient object was seen with just people's eyes?
Well, it's been a few hundred years since we've had one that's really like bright enough that everyone would notice it.
Okay.
The Just in 2023, actually do have a couple or one image about this at some point we can bring back up. But yeah, at 2023 there was the nearest supernova that we've had in a while, but that was still kind of easy to see with a simple telescope, too faint to see with your eye.
Okay, gotcha. Okay. So that's a really good segue into my next question, which is now we've got the James Webb Space Telescope up and running in the infrared. We have had Hubble up there and many other space telescopes as well as ground-based observatories. But specifically for Webb, what are we able to do now by with studying transients that you weren't able to do before Webb launched? And also a secondary question to that is why is infrared important in that research?
Great, yeah. So for the audience in this new format, I have some visuals for various questions, either from you or from Quinn, and so I'm going to go back and forth a little bit. So I'm going to show some now that are relevant to this topic. All right.
Yeah, as Justin sets up here, I also invite the audience to again drop questions into the comment section on the streaming on YouTube. State your question and let us know what part of the world you're tuning in from. And we have our team in the wings here helping us navigate this virtual environment, and they'll be feeding us questions. So as they come up, ask us, and we'll feed them along. Go ahead, Justin.
Cool. Yeah. So seems like a good time to. I have some graphics showing kind of like the progression of what telescopes have given us over time to really hit home like what James Webb is doing for us, and particularly in the transient side of things. So we talked for a minute there about early astronomy and what you could do with your eyes. And so a question you might ask, which you sort of did, is like what's the most distant objects that we were able to identify with just our eyes. The keyword there for a second is identify, because I just said that we saw supernovae that we didn't know were supernovae, right? So those were obviously further away, but the important thing about astronomy is looking at things and knowing what they are, or at least learning what they are. So the answer to that is Saturn. So with our naked eye, Saturn was the furthest object we were able to identify as a planet. And that was 4,000 years ago and roughly 746 miles away, depending on the time of year. And so to get up to like what James Webb's doing for us, I'm just going to make a little analogy, which is seeing Saturn with your naked eye is the equivalent of looking at your phone right against your face. So that's going to be our starting point for this. And then with the creation of telescopes, which were kind of in the early 1600s, just the simplest possible telescope, we already were able to expand that view to things like stars close to the center of the Milky Way, which was something like two bunch of zeros miles away, the equivalent of pushing your phone out to about 70 feet. So that just should kind of show that telescopes were a major step forward in general, moving your phone from here to being able to read it 70 feet away. And then large ground-based telescopes were kind of the next big step, early 1920s. And Edwin Hubble, which of course the Hubble Space Telescope is named after, used these to identify for the first time that there were galaxies outside of the Milky Way. There weren't just stars and planets within the Milky Way, but there were in fact galaxies. So this was not the image that he took with with the Hooker telescope, but this is the Andromeda Galaxy from the Hubble Space Telescope. And this is just an example of this is, it pushed our frontier of how far we could kind of identify things to galaxies outside of the Milky Way. And that is a bunch of more zeros on the end of a 2 miles away, the equivalent of looking at your phone half a mile away. So even by the early 1920s, we were really expanding what we could see to a much larger distance. And in order to talk about James Webb at all, we have to get away from all these zeros and move into what we call light years. So Andromeda is about 1 million light years away. And because of the kind of importance of the concept of light years, I just want to drive home exactly what that means. So the analogy I'll use here is imagine you're on this really cool space train and it's traveling at the speed of light, and you are at Andromeda and you want to take that train to our telescope here on Earth. So it's traveling at the speed of light, and it would take 1 million years for it to arrive. That's the million light years. And the interesting thing that this basically creates is that imagine that the conductor on that train was taking the image of Andromeda. So it takes the image and then it travels, for 1 million years, and it reaches our telescope, and then it hands it off to our telescope. That means that the image is now 1 million years out of date. So that's the concept of the further away we look at things with our telescopes, actually the further back in time we're seeing them. So when we look at Andromeda 1 million light years away, we're seeing it as it was 1 million years ago. And that just gets more and more extreme as we go to larger distances. So going back to this being a half a mile away, that allows us to talk about what James Webb is able to do for us. And so, of course, we had large advancements with the Hubble Space Telescope as well, but James Webb has really been able to observe things all the way essentially to the edge of the observable universe. So it's observing things that are, in this scale, 7,000 miles away, and things that have been traveling on that train for over 13 billion years. And to really drive that home, basically James Webb has identified objects that are within 150 miles, if you want to go in that same scale, or 300 million light years of the edge of the observable universe. And that's just something that has not been possible in the past. You mentioned right at the end of your question, infrared light. So that there's basically two reasons why this is a whole new frontier with James Webb. One is its sensitivity. It's able to see things that are so faint that they're just below the threshold of what we would have been able to see with things even like the Hubble Space Telescope in the past. And then also it's the wavelength of light, as you said. So this is a little graphic to just show this. So imagine you're in one of these galaxies that's very far away on the right. And maybe this light here, this wavelength of light, is maybe optical light, maybe at the same wavelength that we see with our own eyes. As it travels through space due to an effect called cosmological redshift, this light basically gets stretched out to longer and redder wavelengths. So it kind of follows this type of stretching effect. And you can see as it goes through space, it basically just gets to longer wavelengths of light, which brings it from optical, maybe blue, green light, to red, to infrared. And so in order to see these really far away objects, you have to look in the infrared, which is, first of all, only possible really from space, and was only sort of touched on by Hubble. So James Webb is the first opportunity at these types of sensitivities, to see things that are at such a great distance that the redshift effect pushes it beyond what any telescope has been able to really see up until now. So it's a whole new, basically, space of discovery.
Right. So we're really looking into the universe, into the past in an era that we haven't been able to explore before Webb, right?
Yeah, exactly.
Yeah, yeah. Oh, thanks. I love that analogy. Thank you so much. Now I have something to use. Everyone else has something to use when we're talking about like how far away are we really seeing with James Webb. So again, welcome everybody. Please keep on putting your questions into the comment section on YouTube. So Justin, we've been talking about supernova events, objects. So many people might have heard this word, but could you explain, just so we're all on the same page, what are they exactly? And are there different kinds or just one kind?
Yeah, absolutely. So, I mean, of course, you can go as deep into this as you want to go, but I'll give an overview
Let's be
of
top
top
level.
level. So, at the most basic level, I'll show some more graphics on this. So, at the most basic level, this is what we look at for a supernova, and I'll go into details of what they really are. But here's sort of some blobs of light that are really part of a galaxy. It's a nearby galaxy, so this is just kind of the corner of it. And this is like just an area of the galaxy where there doesn't appear to be anything. This is just a kind of a blank area of the galaxy. And then suddenly something appears, and you can see it brightening over a period of about a few days or so. And this is what a supernova sort of looks like. It's not there because it's just a star, and it's too faint and small to see even with something like James Webb in most cases, not in all cases, but in many. And then it explodes and it becomes so bright that we can observe it with even small telescopes, and as we said, in rare cases with your own eyes. So what are these supernovae, and what are the different types? So like I said, it gets kind of infinitely complex, but at the top level, complicated diagram, don't worry, going to go through it. At the top level, we can split supernovae generally into two major groups. So on the left side, this group is stars that start out as this symbol here, M with the O thing, means the size of our sun. So on the left here is things that are less than about 7 times larger than our sun. So our sun would fall into that category, of course. As it progresses through its life, it doesn't actually just end in a supernova, as is sometimes thought, that our sun will turn into a supernova. Instead, it's too small. It actually just ends up kind of running out of gas in the core and turning into what we call a white dwarf. So it's just kind of cooling off and shrinking over time. It takes a very long time for that to happen, but eventually this is where it ends up. And if it's alone, if it's just like our sun, just kind of alone in space, no neighboring stars, then it will just kind of cool off and slowly die that way. It won't explode. But if it has a companion star, and I have kind of an animation of this in a second, but if it has a companion star, and that star could be another white dwarf near the end of its life, or it could be just a regular star, then it sort of steals mass. It steals energy from that other star until it has enough to explode by itself. And so that's what we call type 1a, even though it looks like an I, it's a 1. So type 1a supernova, this is one side of supernovae. On the other side, massive stars, so ones that are larger than, say, 7 or so times larger than our own sun, They basically continue to build their cores up over time. So this is just kind of a cartoon of one of these stars building up layers of its core over time. And eventually that core gets too big, and it basically collapses under its own gravity. And we call that a core collapse supernova event. And this is sort of the other side. So there's a bunch of subtypes of these supernovae in these two groups, but this is the two big pictures. So I have little graphics of what these look like. Obviously, they're artists' representations, but just so you get to the idea. So a core collapse supernova is just a regular star. It's very large, but it's just kind of sitting there, and then it just kind of suddenly explodes because of this core collapse. And then this kind of expanding thing here is what we observe as the supernova. And what's left could be a kind of a remnant, faint little star, or it could be even something like a black hole, depending on whether we actually see a supernova or it just directly collapses into a black hole. But so this is, in this case, a little star remnant. So no neighbor, just explodes out of nowhere, sort of. The type 1a supernovae are these ones that have the neighbor. So you can see here, these are kind of stealing this mass, stealing this energy from a neighboring star. It's building up this energy over time, and eventually it builds up enough that it causes this runaway explosion, which is sort of this completely different thing from the core collapse. And these are particularly special and interesting. Happy to answer follow-up questions on that. But these are kind of the big picture categories of supernovae.
Yeah, that's those illustrations remind me of long ago in my youth studying two objects orbiting around each other. So I think there's many kinds of varieties that can orbit around each other, but particularly here, having that white dwarf around something bloated. There is a question from one of our viewers about this type 1a supernova. So one of our viewers from Canada is asking, and maybe you can expand upon the different things that come up here. How is JWST, James Webb Space Telescope, improving our ability to calibrate type 1a supernovae as standard candles? So maybe you can share what standard candles are at high redshift, and what challenges remain in using them for precision cosmology in the early universe.
Wow. Took that right out of one of my abstracts or something. I don't know. So, great question, and something that is very near and dear to my heart. So I'm happy to talk about it. Actually, the next slide I have that I wasn't going to go immediately to, but happy to, it explains the standard candle thing a little bit better. So the idea that makes type 1a supernovae particularly special and very useful for astronomy is that because of this unique mechanism for explosion where they steal this mass and it reaches a specific kind of runaway point and then they explode, that point is always sort of the same. So these supernovae always explode with roughly the same amount of energy, which makes them roughly the same brightness. And so what that lets you do is imagine these are both type 1a supernovae, and they're at the same distance, so they're the same brightness, because that's what we call the standard candle. They're a candle that is the same brightness no matter where they are, and so when they're next to each other, they look the same. Well, if you then move one so that it is further away, then it's fainter. That makes sense, but isn't always the case. Maybe the object that's fainter is just intrinsically fainter. It's not as luminous as something else. You put our little sun at the same distance, or closer, than a much brighter star that's further away. They might look the same distance because they are roughly the same brightness, but in fact, one is just much brighter and further away. So by using type 1a supernovae, we're able to actually measure distances by identifying how bright those supernovae are. So I will answer this question, but I'll give a little bit more background on what they're really asking about. You really asked the question that is like exactly these slides that are right next to us. So I'm just going to keep going through some. So because we can measure these, because we can measure these distances, how bright is the supernova, therefore how far away is it? These have been used for years as distance measures. So a plot here, but still quite simple. The x-axis is just redshift. So we talked about basically how much light is stretched into redder wavelengths on the x-axis, and then distance measured from type 1a supernovae on the y-axis. So these colored points are just individual type 1a supernovae measured over time. And these were used in the late 90s to compare to these lines, which are different models of what the universe might look like. And this is just relative to those models. If you look at these different lines, these are a few different models. This was what was, this little bump here was what was used to basically identify this sort of like kind of well-known model for the universe these days, is that we have this kind of dark energy, which is a large portion of the universe and is still not well understood. And then these other components, dark matter and regular atoms. And this was the discovery of accelerated expansion of the universe back in the late 90s. And this was done with type 1a supernovae, at least part. And so these are extremely valuable for this reason. And for the last 20, 25 years or so, these have continued to be used for this purpose to refine these measurements. And so then the question is, that the question that was just asked is, how is James Webb increasing the precision on these measurements basically, and how is it helping us learn about type 1a supernovae and use them as for cosmology at higher redshift. So for the first part, there's a couple ways. One is it's being used to, I don't really have a slide on this, but I'm happy to just say it. It's being used to kind of start knocking off some of the possible unknown uncertainties that have been listed over the years as possible issues with the way that type 1a supernovae are used for cosmology. So one example is that the type 1a supernovae have to be sort of calibrated with some closer by thing that we can measure distances to. And we use these stars that change their brightness over time called Cepheids. And there was a long-standing kind of discussion about these, that maybe our measurements of those were not accurate enough because, well, actually, basically because they looked something like, I have this slide from earlier, something like this. We're using these nearby stars where they're in a giant field of stars. And so there was a concern that they're basically overlapping maybe, and so we aren't able to accurately measure the light from just Cepheids, these special variable stars, and therefore they could be biasing our cosmological measurements. So James Webb has much better resolution than even Hubble, and so James Webb has basically been going back and remeasuring these Cepheid brightnesses, and was able to confirm that those were fine. That was not causing a significant problem for the cosmology of type 1a supernovae.
Question, while you have this up, how is it that you can tell the difference between a point of light that's a supernova versus a point of light that's a star, if they just look like points of light, whether they're close by or far away? Like how do you distinguish that?
Yeah, so the answer is that it is extremely difficult with only a single image or a single point in time that you're observing a given point of light. And so basically the answer is you have to observe the same patch of sky multiple times and see what changes. It is sometimes possible to sort of guess that an individual point of light is a supernova, maybe based on its colors, or maybe based on its proximity to a galaxy or something like that. But in general, you really have to just keep looking at it for a period of time and see if it changes. And that's really what we do.
Thank you. Okay, so I got another question from the streaming comment section. If one were to look at the farthest object that JWST can see in a visible color now, how far up in the UV would the original emission would have let me repeat that again. If one were to look at the farthest object that JWST can see in a visible color now, how far up in the UV would the original emission would have been emitted originally to be redshifted?
Right. So there's a couple of answers to that. because James Webb has different instruments for different things. So at its absolute reddest, it sees things that are about 25 micron or so, which is quite red, and quite far into the infrared, I mean. And then I guess the question is sort of like you have to go one way or the other. You have to either you have to either say this thing is emitting in the ultraviolet. At what redshift could we see it until? Or I want to see something at redshift 10. How far into the UV can I see it? So I can answer both those, I guess. So say you were interested in something that was at around I don't know what, like zero point 0.1 or 0.01, so like 1,000 angstrom. So basically, the visible light is kind of just on the red side of this. Then you could see that all the way to, I could do a quick bit of math here. So it'd be like 1,000, say, yeah, so it'd be like around well, basically redshift whatever you want. So I mean, for 25 micron, you can see things all the way out to say redshift, like I mean, well beyond redshift 10 into redshift 100 or so. But they're going to be so faint that that instrument is just not really sensitive enough to do that.
Mhm.
More likely, we'd be using what's called the instrument called NIRCam to see these really far away things. And that's limited to 5 micron. And so if you had something that was, also emitting in the UV, then you could see all the way to redshift about 50
Mhm.
with that. So you
And
have to ask, yeah, one direction or the other, I suppose.
right, right. And the most distant object, I believe, is out to redshift. Confirmed furthest object is around a redshift of 14, I believe.
Yep, yeah, we're at about 14, and that's a galaxy, not a supernova. And that is just because of it's just they're very faint as well. We might be looking in the right wavelengths,
Mhm.
but they're very faint, which is why I said, the 25 micron instrument MIRI, technically it has the wavelength range to see to these kind of absurd redshifts, but it's not as sensitive, so you actually kind of get limited to lower redshifts.
Well, I think this whole conversation is another nice segue to this image that you see in the back of my background. It was also the advertisement, the video, and I'm sorry, the image in the talk advertisement. And so in this background, there's a whole bunch of white things and orange stretchy things. So I would love if you could maybe bring up that image and talk about what we're seeing, and why it's really useful in your area of research.
Yes. So first, I can show this is a different version of the same image, so everyone can see what we're talking about here. But then, yeah, to explain this, I'm going to have to go through a couple of figures. But I'll say at the top level that this is an example of gravitational lensing. So I'm going to show kind of like how this happens, but just so you have this in your head. The things that are white here in these, so I wish I could kind of draw on this, but anyway, so this is like a big gravitational lens kind of in this region, and then also in this region. And the things that are white are actually like in the foreground, and they're doing the lensing of all these kind of red background galaxies. And so things like this and this, I think you can see my mouse, hopefully, are galaxies that are behind these big bright white ones and being gravitationally lensed. So now I do have a couple slides showing kind of how this works. Um, so this is the concept of gravitational lensing in general is, first of all, really cool. I think it's one of the coolest things in astronomy that actually like works, and we've observed it and we can use it. I think it's really really fun. So the idea here is that matter kind of tells space how to curve. and like it bends space-time in this way, and then that tells matter, or in our case energy like light, how to move. So it kind of gets bent around massive objects. So in video form, imagine you've got a galaxy, or in the other case a cluster of galaxies, but it works the same way, something massive that's between us and some background object, and the light from that background object gets kind of bent in this way around this massive thing in between us. And the result is that we can actually see multiple images. This is a real image up here of the same thing. And if those are kind of misaligned so that one path is longer than the other, then when light goes along those two different paths, they can actually arrive at different times. And so this concept of gravitational lensing causes both multiple images of background sources, one along this path and one along this path, and a delay in the arrival time of those images is first of all really cool, I think. And so then the way that I am kind of interested in gravitational lensing, and specifically that image, which I will get to in a second, is what happens when back in this background thing, there's actually a supernova, not just a galaxy or something like that. So that happened for the first time in 2014. This is a galaxy with this yellow thing is a supernova, and it's split into 4 images of the same supernova in the background, and in fact a 5th one up here. And the reason this is interesting is because if you can identify what that delay is, how delayed these images are, then it's kind of like a direct measurement of how fast the universe is expanding. I'm not going to get into the details of the math how that works, you just have to trust me. But it is a unique kind of alternative to things like type 1a supernovae, which also measure this kind of expansion rate of the universe. So for this object, this image that you're showing, this little arc here of bright red things is actually 3 images of the same host galaxy. So I'll show you zoomed in here. So you can see this is actually the same galaxy 3 times, and it's just being split into 3 images by this gravitational lensing effect. And here you can see better that these are all doing the lensing, and then there's various other lensed things in this image here and here. And then this here on the right is showing this blue dot is actually a supernova going off in that galaxy at the time that we happen to be taking the image. So this was a very rare opportunity, because this is not just a regular supernova, but actually one of those type 1a supernovae. And so that was this was a James Webb discovery that was kind of one of those mind-blowing ones that was really exciting. And then one more cool gravitational lensing result is this other galaxy cluster. I'll show another cool image here. So this is another cluster. So you can see here, these are again doing lensing. This is a Hubble Space Telescope image from 2016. So these are the things doing the lensing again. And then these are again multiple images of the same galaxy, and they're being stretched out by this gravitational lensing effect. So there's one here, there's one here, there's one here, and this is another one of those gravitational lens supernovae, which was called supernova requiem at the time. And this cluster was special enough that it got a new image with James Webb in 2023, and there was a new supernova there. So you can't actually see the scale. You just have to trust me that these white circles contain a very faint supernova. Yeah, the James Webb discovery of 2 gravitational lens supernovae coming from the same galaxy, separated by 7 years. And because of this time delay effect of gravitational lensing, this supernova requiem is actually coming back. So we plan to look at this cluster again in 2027 with James Webb, and hope to see this coming back now over a decade later. So this is just one of those really cool things that is really only possible with James Webb as well, because of its sensitivity.
Yeah, that's just so cool. That galaxy that's stretched at kind of that 10, 11 o'clock hour, is that the same galaxy
Yeah.
uh, imaged along the bottom?
Yeah. Yep. They're labeled on this side. So there's 5 images of the same galaxy here, and they're just really wildly stretched by this gravitational lensing effect. So this D image is where supernova Requiem will reappear in a couple years now, year and a half or so,
Hmm.
and then it will actually reappear again much later in another 20 years or so as the light goes through this really deep part of the lens of this gravitational lens in the middle here, and more like 2050 or something. But
Hmm. Yeah, it always blows my mind on how precise and how we can use the concepts of um, stretching of space time from massive objects to do amazing things like this. Um, so, why do you want to study these things? What's so interesting about it? What motivates you to study these supernovae in general, but specifically with Webb?
yeah, so this will actually probably tie back to that original question from Canada about high redshift type 1a supernovae. But in general, I'm very interested in basically using supernovae to understand both how the universe is changing over time and
Mhm.
also what the universe looks like kind of in the early days in areas that we have not been able to really look at in detail until Webb.
Mhm.
And so, for example, on the supernova side, you can imagine that we are very interested in what kind of the first stars were like in the very early universe. There's even with Webb, those are really too small and too faint to look at individually in detail. But when they explode, we can detect them.
Mhm.
And so these really early universe stars are when they explode are kind of a unique way to understand what's going on in the early universe. So we're very interested in that. Um, and then on both the lens supernova and the Type 1a side, it's about cosmology. So understanding how the universe is changing over time and what it's really made up of. And so I sort of hinted that yeah, these lens supernovae are a really cool kind of direct measure of the expansion rate of the universe. The Type 1a supernova side, which there was this question about how we're using Webb to understand Type 1a supernova over time. That's what I specifically am interested in, which is really identifying the first set of Type 1a supernovae that are in a distance range that we've just never been able to look at before. So we've just never been able to identify any Type 1a supernovae before beyond about redshift 2 or so. And
What's that look back time for Redshift 2?
that's getting into, oh, actually, I have a slide for this. So let me,
Oh, I can never Redshift to me
yeah,
makes sense, but I know that's a weird number. So
uh,
look back time it is might be a little bit more
yes, one
less
second.
abstract, I should
It's
say.
actually 1 second here,
Yeah.
right here. So this is the same thing of redshift, so the stretching of light
Hmm.
as a function of distance, but it's our current set. So that one I showed was in the late 90s. So this is the age of the universe here on top. And
Gotcha.
this is the green ones are the ones that we're just starting to get with James Webb. So we're reaching this sort of like, it's a few billion years old age. And we were really restricted to about, 5 or 6 billion years old until this. And that's just due to the wavelengths of light that we observe at, basically.
Okay. Wow. Yeah, and you're just getting started. Um,
Yeah, we are like some months into building the sample, and we have about four now that showed
mhm,
two, but two are not published.
mhm.
Yeah, so this is just showing sort of like that Hubble was able to get us to about that kind of 5 billion years old range, and now we're really just starting to get into this a few to 1 billion years old, and we have found a bunch of objects that are in this range now, but not so many Type 1a yet.
Right, right. Yeah. Okay. So the search begins. We have a question from the audience. If the light from a supernova comes at a different time due to the curvature of space, how do you know it's the same supernova? That's a great question.
That is a great question. Yeah, that's actually a really cool question. So, especially because I just said that there were two supernovae in the same galaxy for, in this case. So, how do we know that in the other case it's the same supernova?
Mhm.
So, there are a couple of ways that we know this. One is that we have actually quite good models of how gravitational lensing works. And what we can do in most cases is we can take an observation like this and a model for what this lens, how this lens is impacting light, and trace back, do we think all of these supernova images that we see, do they all come back from a single point, or do they come from multiple points? And in all cases so far, they've come from a single point, and so we can identify that they're either the same supernova or two supernovae going off in the same place at the same time, which would be very surprising. And then
Mm-hmm.
the other way is we observe them for a while. Maybe we get we look at their colors over time. Maybe we look at their a spectrum of the supernova and identify its brightness or as a function of wavelength. And we can then identify that these are really the same supernova. They
Mm-hmm.
look identical once you look at them for a period of time. Even if at the moment that you first detect them, like here, this one's very blue, this one's red, this one's also red,
Mm-hmm.
they look like different supernovae. We're able to trace them back in that way as well.
Okay, so would another way to state that is, I got up this morning and combed my hair. Maybe I combed this side and that side and did whatever else, brushed my teeth. So if you see myself doing that again in the same sequence, that could mean that it's the same event happening again, just later on, right? Is
Yeah,
that
yeah.
what
I
you
actually have
say to
this
that?
slide as well. This might be useful,
Okay.
which is this is so we have the same thing, three images of a supernova going off.
Mhm.
And if you just stared at this, then you would first see the light from a maybe getting brighter and then getting fainter again.
Yeah.
Uh, but then you would also see later getting brighter and then getting fainter. And while they might be different brightnesses because they might have different levels of magnification from this lens, sort of like the shape of this behavior will be the same. It'll be exactly the same because it's the same supernova. And so by doing this for each of these images, we're able to identify that they're really the same thing. We're just seeing them at different times and maybe different brightnesses.
Okay. Um, Okay, I'm still it's I love clusters. It was
Yeah.
something I did in my work, but the gravitational lensing side and the mathematical modeling, that wasn't my thing as much. But the clusters themselves are they're just so beautiful.
Yeah.
So I have one last question before we kind of talk more about your career background, kind of where how did you get to your along your journey, how you got to your current position here. So what would you say is one of the most challenging aspects of your research, and challenging aspects even about Webb and using it to do your research?
Yeah, so I'd say the most challenging thing about this research specifically, which is focused on both these sort of gravitational lens supernovae and identifying these really far away, say type 1a supernovae, is that sort of by definition, we're trying to push the frontier into the unknown, and that unknown is only observable with Webb. And so there's no help from other resources. We can't with a lot of science you might find something interesting and then observe it with everything that we have: ground-based telescopes, Hubble, Webb, X-ray, whatever. And in these cases, it's the only resource that we can use. And so there's difficulties with scheduling all these observations. We're trying to observe lots of things. In fact, if anyone goes and looks at the schedule for the next 2 weeks, we just blew it up with 6 different supernova observations in 2 weeks,
Wow.
which we have to go thank the schedulers for figuring out how to do. And these are all they're sudden. This is not something that we can schedule in advance by a year. These are things that we have to say, uh-oh, we found something really interesting. I'm sorry, only Webb can observe it. And so we need you to stop what you're doing and observe it right now. And sometimes, Space Telescope decides that that's worth it, and sometimes not. And because it's the only resource capable of doing that, there's no second chance. There's no other thing we can go to say, okay, it didn't work with Webb, we'll do it with something else.
Mhm.
And so that's difficult, but also kind of exciting in that everything that we're doing is unique to Webb. We can't do it with anything else.
Great. Yeah. I know the interest of the astronomy community in using James Webb is huge because it is meant to do this groundbreaking work that you and your team are working on. So yeah, I can't wait to hear what happens as things, you uncover really new, interesting supernova really far away, and we hope to hear about it in the near future. So let's start to move into the very last section, maybe about 5 minutes or so, because I know there might be some younger career folks, some high schoolers, college students listening in, getting really excited about, hey, I could be a future user of James Webb. I was looking at your bio, and looks like you studied mathematics, and then you went to the dark side before going to astronomy as well, looking down at the Earth versus away, analyzing land images from space. So I'm curious to, yeah, can you share how those past experiences really helped you in where you are today in your professional career?
Yeah, I think it's actually I don't know, it's maybe a helpful track for people who might be interested in getting into astronomy, but didn't think about it early enough. So I did not study physics or astronomy in my undergraduate at all, which was not advisable for a career in astronomy. And so basically, yeah, I took an internship in the Earth Science Division at NASA, studying, as you said, using satellite imagery to identify landslides. And it's actually not that different from astronomy. It's still a lot of using computer programming and maybe some statistics or something to basically get information out of images. And all that kind of experience of data processing and programming was directly useful. And basically, the only way that I was able to, break into astronomy is by just kind of saying, "Hey, I know I don't really have the physics and astronomy background, but I can do research, and I can do research that's similar to what you need."
Mhm.
And then I kind of picked up the academic side on the fly, and all of that kind of intensive um, learning of all these things that are still needed, programming, the math for the type of analysis that we do, and these kind of image analysis and data processing things. It's really the same. So that was a great basis. That was kind of something that people can do even on their own time, is teach themselves some programming. All the NASA data is public; you can download it, and there's a lot of resources for analyzing it. And
Mhm.
that's essentially what I did. So
Mhm. So yeah, so it sounds like you got bit by the astronomy bug a little bit later in life. But that science, mathematics, that was always there, it sounds
yeah,
like.
I mean, I would say that I definitely had a love of astronomy from, as I said, or as you said, growing up in rural Maine and getting a lot of stargazing time.
Mhm.
But I think that coming from that background, a career in astronomy just wasn't really one of the kind of common paths on the table. And so it's not that I wasn't interested in it, but it's just it didn't really um, you know come to mind as a real option until much later.
Yeah.
And by then, I had to find an alternative path.
I think in some ways you and I are reversed because I grew up in a very densely populated metropolitan area and like saw a star, which I learned was actually Jupiter. It wasn't even a star at all, and that was my view of the universe, and it was still enough to get me hooked. As even with one with one little thing out there, when there's much more. So last question here. So, what are you looking most forward to in this new era of astronomy with Webb? Maybe in general or in your field?
Well, certainly in my certainly in my field, we are. I'm extremely excited about not just continuing to push, further and further distances, but I didn't, really talk about that there are types of supernovae that are still theoretical.
Mhm.
There are types that are still they should exist. We expect them to be there, but we have not been able to see them because they will only happen in the early universe.
Mhm.
And it's only been a few years, but we have looked. We have not yet found any. And that's one of the core mission objectives of Webb is to detect some of these, which in many cases are these explosions of the first stars.
Mhm.
And so I'm very excited. I'm sure we will find them. They must be there, but it's
Mhm.
going to take a kind of dedicated effort from both Space Telescope Science Institute and the transient community to make that happen.
Right. Yeah. I was reading that in the some of these galaxies that JWST is finding, they're already finding that they're metal rich. And
Mm.
so supernova have to have gone off prior to that, right? To get these metals into, metals, the irons,
Yeah,
the carbon, the nitrogen, all iron, according to astronomers, into those systems. So you're trying to find those
yeah.
early ones, right? That did the polluting of the
Yeah,
first
we
galaxy.
didn't talk about that really, but yeah, that metals in general, heavier elements in general, come for the most part, supernova explosions. And since we have those in the relatively early universe, we know that in the very early universe, there had to have been supernovae, and we just
Mhm.
have not yet found them. The most distant that we've found so far um, is at about redshift 5 or so, which is still, the universe is still a couple billion years old. So uh,
Right.
pushing back beyond that, kind of early, back beyond a billion years or old or so, is like the holy grail that we're kind of going for here.
Right. That will be amazing.
And
We'll have
and one more thing, which is that it's really only possible with Webb, even with upcoming things like Roman,
mhm.
that just because of the wavelength range, it's going to require Webb, so we got to do it while we can.
And this is the Roman Space Telescope, NASA's next flagship mission that
Yeah.
will be launching in the next, uh, gosh, 2 years or so. Yeah. All right. Well, um, I think we are now ready to do the question and answer session. So if I can invite Grant, one of our team members here, to turn on his camera. Um, And this portion will be very similar to hi Grant, how it's played out with our previous public lecture series. So, Grant, how's the comment been going on the YouTube stream?
Oh, it's been really good. I mean, you've seen a couple of the ones that I've picked out so far. Um, Definitely some returning people from the previous PLS, and they always come locked and loaded with some phenomenal questions.
Yeah, yeah.
Usually, based on how much it derails you, is how you know how much of a good question you have in your thought. One thing I did want to ask before we get started on some of the audience questions is we always allude to, but never really outright state something that I find the most interesting because, kind of like you, Justin, I come from a non astronomy background and got into the field um, and just have tried to learn everything that I possibly can. But learning about early universe, especially like early supernovae and early events, we're looking back in time. And the further away we look, the further we look back in time, which is a simple statement to make, but a very difficult concept to understand. And everybody who comes talks about the formation of different things. So if you could expand a little bit more about how time as distance and distance as time plays into the way that you choose what you observe and learn from what you observe, I think the audience would really enjoy that.
Yeah, so I will quickly show the same this animation quick just to reiterate this and maybe also for the people who probably joined a little bit later, but and then I'll talk about how that is relevant. But so yeah, the concept of the kind of time distance connection is this concept of light traveling across these light years. So I had this little just small recap, this idea of being on a train that travels at the speed of light. And these objects that we're talking about are millions or billions of light years away, the distance that light travels in a year. So if you're on the train and you're traveling from one of those objects to us, it'll take you millions or billions of years, depending on how far away it is. And so the concept of looking back in time comes from the idea that, let's let the train run, and then the idea that if you are on that train and you kind of take a picture and then bring it to us, which is essentially what's happening when we look at things with our telescopes. We are looking at light that has traveled this whole way. It's essentially the same as if you were on this train, you took a picture, and then you traveled to us and you handed it off. That picture is out of date by a million years in this case. And so the further we look away, the longer it takes the train to get here, and the older the image is. And so when we're showing these things about, the universe is 5 billion years old, the universe is 3 billion years old when the supernova went off, by the time it reaches us, whatever it left behind is now billions of years out of date. So we see that galaxy that the supernova is coming from as it was, 8 billion years ago. And so that's the concept. And the further back we look, the longer that look back time is. Does that answer your question?
Yeah, absolutely. So I'm gonna throw you a good one here. Why do you think that the Hubble constant value from the supernovae measurements is different from the one calculated from the cosmic microwave background, the CMB?
Lobbing the grenade right in.
I think you would have a Nobel Prize if you knew that answer, right?
So there's a couple answers. The first answer is, if I knew the answer, I'd have a Nobel Prize. And the kind of larger answer is, and the small amount of background for those not specifically familiar with this Hubble tension is, I mentioned briefly that we've used type 1a supernovae for years to measure the expansion rate of the universe. And that's nearby. We're looking at how fast the universe is sort of expanding now. If you do the opposite and you look at the very early universe, and then you come up with a model for how the universe works, and you put those together and you predict what the value, how fast the universe is expanding now, and you compare those, then they're actually quite different. They're different by enough that we call it the Hubble tension. That parameter is called the Hubble constant, and in some cases the Hubble crisis. And it's one of the most kind of active cosmology questions today, because the answer is either there's something wrong with type 1a supernovae. There's some missing uncertainty that we are just not grasping, or there's something wrong with our cosmological model that basically makes the prediction from the early universe to today. So I'm personally trying to answer that question by basically using Webb to find these very distant type 1a supernovae, because the idea is, if type 1a supernovae are maybe, say, changing the further away we look at them, then that could mess with our kind of local measurement at a very small level, but at the level that we're talking about for this type of question. And if they're changing as a function of distance, then the further away we look, the more different they should be. So basically, we're looking for these really far away ones as kind of smoking guns of the fact that they may be changing across this entire region. So far, with a relatively small sample of a few, we haven't seen any significant deviation. So that doesn't seem to be an immediate answer to the question. And there have been kind of exhaustive studies into what could be the answer. And basically, the other angle we're taking with it is with these lens supernovae. So, like I said, these also measure the expansion rate of the universe. They're also measuring this Hubble constant, but even though they're also supernovae, even if they're type 1a supernovae, it's completely unique from the normal type 1a supernova measurements. And so we're basically trying to figure out, okay, if we do it a completely different way, we're not using type 1a supernovae in the same way at all, do we get the same answer, or do we agree with the early universe modeling method? So far, we've had two, and one has agreed with each. So basically, we need more of them. We have found one more, and we're literally in the process of doing that measurement right now. So stay tuned for the tiebreaker. Yeah, that's sort of the other way of doing it. So the answer is we don't really know, but we are trying multiple ways of identifying what that cause could be.
So, question, Justin, with using these multiply these gravitationally lensed supernovae, are you able to, because the time the difference in the arrival time of the supernova to us, is that probing the space that's being probed along those different lines for the different supernova, that's allowing us to observe to detect the expansion rate in those unique curvatures? Is that correct?
Yeah, exactly. So if you're anyone's interested, you can go Google something called the time delay equation, and basically it relates the Hubble constant, which is this measurement, this parameter that we are trying to measure, to basically a variety of things that include that delay in arrival times. You need to measure that.
Mm-hmm.
The kind of characteristics of the lens, which I said we're pretty good at modeling, which is true. So you have to kind of get a model for the lens, measure that delay in time, the delay in arrival times, and then kind of encoded in that equation is the distance between us and the lens, the distance between the lens and the supernova, and the distance between the us and the supernova. And all of that has information about cosmology. And if you have the good model of the lens and you have the measurement of the delay in arrival times, you kind of get the other side of the equation, which is the Hubble constant.
Oh, interesting. Yeah, I know one of with cosmological models and cosmological parameters, being able to get to the answer in multiple ways really shores up a value that you look at. So having this different novel way is really good for that piece there.
So forgive me if this is a little more layperson, but when you're doing gravitationally lensed observations, is it still traveling the exact same distance, or are you observing it at different relative times because you are altering the path that the light is traveling to get back to you? So are you observing it at like X year here and Y year here and Z year here?
Yeah, so I think I got that question, which is basically, yeah, so the time delay, delay in arrival times has two parts. One is the kind of obvious, which is the kind of geometric difference, right? Like one is being deflected much more than the other, say. And so you just like, wouldn't just generally think, okay, it's being deflected more, so it's going to take longer to get here. And that's true. But then the other part is that the light has to climb in and out of different levels of gravitational potential. So on that slide showing, I very quickly can show
Curvature.
the curvature slide.
Yeah.
So in this example, I can do this. Depending on how big this thing is, and whether the light is going, let's say, through here or right down the middle, it takes longer for light to climb in and out of this deep well than if it was coming over here. So while the delay from being deflected, wider around here is going to be longer than being deflected through here, actually the delay from going through this deep gravitational well dominates. And so they both contribute, but the ones that come through this kind of center part of the lens end up being delayed more, which is why in this case of the arrival of Requiem, these ones that are deflected out here arrived earlier, and the one that's coming right down through the middle of this lens is the one that's taking 10 years to arrive.
Okay. All right. Yeah, you answered the question and another one that I didn't have the right words to ask. That's awesome.
It is awesome.
So follow up, according to the supernova Hubble, the supernova value is faster than the CMB. So is the expansion even faster than the dark energy force?
So I think the question is basically saying, oh, I see. Right. So This is basically, I think, asking like what the fate of the universe is essentially, right? Like that's kind of what this is getting at. Like, are we gonna kind of outrun dark energy and or whatever? Like we're gonna they're kind of three fates, right? Like either eventually dark energy kind of like runs out or whatever, and we kind of like maybe collapse back in, or maybe dark energy is kind of staying constant, and eventually we just kind of expand into nothing, or maybe dark energy is getting stronger with time, in which case maybe we tear apart. So these are kind of the three possible scenarios, and in terms of the expansion rate, that doesn't specifically tell us that. We have to look at like kind of the history of expansion over time and see and compare it to dark energy. And right now is actually a very interesting time to be asking the question, because if you'd asked it about a couple of years ago, we would have generally said that the dark energy staying constant answer was correct. That it looks like it's just kind of constant, which would mean that the fate of the universe is that we'll just kind of float apart, and eventually you won't be able to see any light from anything else because we're too far apart. But the most recent measurements of this are starting to suggest that maybe dark energy is changing with time. And it's exactly the goal of the Roman Space Telescope that we just mentioned to exactly answer this question. Is dark energy getting stronger? Is it getting weaker? Is it staying the same? So we're just starting to get hints, but Roman Space Telescope will answer this question in a few years. So stay tuned for that.
Awesome. Thank you. That's all from the chat, except for one final question that I want to save to the end. So Quinn, if you have anything else you'd like to ask, I wanted to give you an opportunity first.
Let's see. I don't think so. Just looking at my notes here. Well, I guess here, what's the one question, not one, what is one question you think Webb's going to answer really, really well that you've been dying to ask Webb to help you get data for?
So yeah, I mean, again, Webb broadly is going to answer an absurd number of questions really well.
Yeah.
So, you
So you have to pick one.
Yeah. So
Your favorite.
For me specifically, I think that one of the questions that is going to be well, I already said the stuff about early universe.
Right, with the first stars.
That's pretty unique to Webb as well. For me, on the Type 1a supernova side, although things like the Roman Space Telescope, like I said, is very focused on answering these questions about cosmology using Type 1a supernovae, it will not be able to kind of study supernovae, Type 1a supernovae in detail like Webb can, beyond the distances that we're kind of already used to. It's sort of a clone of Hubble, but wider. It sees the same sort of things as Hubble, but just more of it. And so these kind of detailed studies that we're doing into what Type 1a supernovae really look like, and are they the same at all distances? Can we trust them as distance measurements at all distances? Is again a kind of uniquely Webb question. We can't really do that even with Roman or Hubble. And so the kind of sample that we're building now for Type 1a supernovae is like the only sample that will be able to do that. And so it's really important that we do that. And so it should be able to answer this question uniquely with Webb of, are Type 1a supernovae trustworthy cosmological distance measures everywhere? Or do they change with time? Do they change with their environment? Things like this that are really important for this next generation of cosmology measurements.
Gotcha. Okay. Yeah. Again, Webb just pushing into an age of the universe that we haven't been able to explore before, and who knows what we're going to get, and trying to answer those questions like you mentioned. Yeah. So it's very exciting times. And I think this is at the end here. Any last questions, Grant?
Yep.
You
I
did
saved
one more.
I saved this one to the end on purpose. Especially it's a good one to ask in general, but I think as somebody who didn't start in astronomy and came to astronomy, you'll have a very good and interesting answer that will be useful to the audience here. What is your either favorite or your suggestion for a book or author on astronomy for the layperson, somebody who is not an astronomer or is just getting started.
Okay. Yeah, I mean, to be honest, I haven't read those types of books in a while, but but I definitely did back getting into astronomy. I definitely enjoyed some books by both like Carl Sagan and Neil deGrasse Tyson are both there's what is that? Astrophysics for People in a Hurry was fun to just get into a broad range of astronomy topics at a very high level, just so you kind of get like conversational level knowledge in like a wide range of things. And I find both of them to be very good science communicators to the layperson, and still very entertaining for astronomers, I think. So
Mm.
I think there's lots of material to go into with them, and in these days, obviously, not just books, but also shows and documentaries as well.
Mhm. Yeah. Yeah, there are a lot of people, when I was younger, just doing a lot of reading and watching a lot of really good programming to get a little taste of these areas and what's the main thing. Of course, there's lots of things that we do here at the Space Telescope Science Institute and at NASA to really help you as well. But opening up that book and kind of hearing that story unfold, that's always really engaging. So thanks for sharing some of those, Justin.
I also recommend just sci-fi in general for getting into like the general, so, sometimes even science side. Some of those books go pretty deep into the actual science side, but also just like for an excitement of space and astronomy in general is definitely partially how I got into it as well. So.
Mm.
I'll throw myself under the bus. I first got really, really interested when I started reading about the physics and science of Star Trek.
See?
Gotta start somewhere, right, right, Grant? So,
It was great.
it is. I think that book exists somewhere in my
Oh,
house.
it is a book.
Yeah,
Absolutely.
I
Yeah.
think I got it from my husband one year. So, um, all right. Well, if you want to do one last check, Grant, anything else pop up for questions before we kind of close it out here?
Nope, I think we are all good. Thank you everyone in the audience for such good questions today.
Yes, thank you. I'm just going to pop this up again. So thank you to everybody who's thank you to everyone who's been listening in and joining us and sending us questions during the event here of our first deep space dialogues. I really want to thank our team behind the scenes, Grant Justice, who has been fielding questions for us during the entire time here, Gary Gilbert, who's been in the background, and Kelly Leppo and Chris Britt, who will be our upcoming host for the next two deep space dialogues. So we have topics for the next two. So in July, we will be talking about the little red dots that have been found in deep web images. So what are they? They are not Skittles, but you have to come and hear about what they are. In September, we'll be talking about characterizing exoplanets, planets around other stars, and their atmospheres or lack of atmospheres. Which one? You might come listen to that and hear about how Webb is really making some groundbreaking discoveries in that area of exoplanet atmospheres. So again, if you want to get updates on when our next two talks are, when we pin down the dates, subscribe to our YouTube channel here at Space Telescope Vision. You can also look at the stsci.edu website. That is the Space Telescope Science Institute website. Our events are also listed there. So thank you again, and we hope you have fun reading up about any science fiction, anything about Webb and astronomy, and we look forward to you joining us next time. So have a good night, everybody.
Okay. Great job, guys.